talk about hydrodiping, and to do that, you can do a take-home experiment. Now, a couple things I want to show you. This right here is a paper plate. This is made out of the chemical cellulose. That's going to be important later on. Good old H2O. This is water. Kind of non-polar, kind of polar. We'll talk about that in a minute. Here's red food coloring, or red Lake 40. Now notice how well it mixes with the water. There's a principle that says likes dissolve likes. If the water is polar, has a plus and a minus side, to dissolve anything else, that also has to have a plus and a minus side. And quickly you can see the food coloring dissolving. But it's not just are things polar or non-polar, it's a continuum. So here's shaving cream. Number one ingredient is stearic acid, okay, or sodium stearate. So I'm going to put this on here, and it doesn't really initially do much to the paper. Watch what happens when I put in the food coloring. Okay, a couple drops, and it appears the food coloring does not readily dissolve into the stearic acid or the shaving cream. So I'm going to make a design here. Okay, this kind of cool design. I'm then going to take my paper plate, punch down, pull it up like this. But here's the neat part. If I take this off, you can see the design is now on my paper plate. Now I'm going to rinse it real quick. And there it is. Something is going on here to where that dye that was polar stuck to the plate, but not much to the water. Or it didn't, it didn't come off the water or the shaving cream. So the idea is likes dissolve likes. Items that are polar, and we'll define those, stick to items that are polar, non-polar, non-polar. But it's not just polar and non-polar. There's basically a continuum. Some things are kind of polar and some things are kind of non-polar, so they can have properties of both. This is kind of a form of hydrodipping. We're going to do the same. We're going to try to explain this chemically and then do the same thing on a large scale with a pair of tennis shoes.